Good day and hello everyone. We are excited to present a deep dive into artificial potential fields or APFs for robot path planning. Our goal in this video is to walk you through the mathematical foundation, simulation setup and pseudocode behind APF while also exploring its practical limitations. Path planning is a fundamental capability required in autonomous mobile robots. These robots must be able to navigate from a start position to a designated goal while avoiding any static or dynamic obstacles in their environment. Efficient path planning ensures the robot's safety, optimizes its energy consumption, and enable it to perform tasks without human intervention. This is especially important in complex scenarios like warehouse logistics, urban drone deliveries, or planetary rovers.
The artificial potential field approach imagines the robot as a particle in a field. The goal exerts an attractive force like gravity, and obstacles create repulsive forces like electrostatic charges. The robot rolls down to the goal. As you can see in this photo, there is a valley being shown. The robot's starting position is a position of high potential, and the goal position is the position with the lowest potential. The hills in between are the obstacles, and you can see the obstacles have very high potential. The robot will move from the position of high potential to the position of low potential.
Before proceeding further, let us define a few terms central to the APF algorithm. The world space is a complete environment. Free space is where the robot can move, while obstacle space is where it cannot. A configuration describes the robot's current state, which includes position and orientation of the robot. The path is a trajectory formed by sequence of configurations. Mathematical model of APF consists of two kinds of potential. One is attractive potential and other is repulsive potential. Let us first talk about attractive potential. The attractive potential field is designed to guide the robot towards the goal. The equation is quadratic, which means the force increases linearly with distance from the goal. Zeta is a positive constant that scales the attractive force. Q is the current position vector of the robot, and Q goal is the target destination. The difference represents the Euclidean distance between these 2 points. The resulting potential forms a valley around the goal. The steeper the slope, the stronger the force pulling the robot towards the center of the valley. The repulsive potential field is responsible for keeping the robot away from the obstacles. It only becomes active when the robot is within a certain proximity of an obstacle. The closer the robot is to the obstacle, the stronger the repulsive force becomes. Eta is a positive scaling factor that controls how strongly the robot is pushed away. PQ is the distance from the robot to the closest obstacle. When this distance is beyond P naught, the robot is unaffected. This formulation creates a force shield around each obstacle that helps prevent collisions. The robot's movement is guided by the net force derived from both potentials. Mathematically, this is the negative gradient of the total potential. The gradient operator calculates the rate of change of potential, giving us the direction and magnitude of the steepest ascent. We use the negative of this, which means the robot always moves towards the lowest potential energy. This ensures the robot moves towards the goal while simultaneously being pushed away from the obstacles.
The pseudocode of the APF algorithm is quite easy to understand. We start by defining the robot's initial position, goal position, and how close it needs to get to the goal to stop. This is called the position accuracy. In the main loop, as long as the robot is not close enough to the goal, we keep repeating the steps. Now, we calculate a force that pulls the robot towards the goal. If the robot is far, the force is strong. If it's close, the force becomes weaker to avoid overshooting. Then we calculate repulsive forces from nearby obstacles. If an obstacle is close, it pushes the robot away more strongly. If it's far, it doesn't affect the robot much. The total force is the sum of attractive and repulsive forces. This gives the direction the robot should move next. The robot updates its direction and moves forward based on the total force. The motion considers turning speed limits and maximum speed. We repeat this process, calculate forces, and move until the robot reaches the goal or the time runs out. Here is a real-time simulation which shows the robot avoiding the square obstacle and the triangular obstacle. Here is another simulation of the robot reaching its goal. The APF algorithm faces a significant challenge, which is the occurrence of local minima. A local minimum occurs when the attractive force towards the goal and the repulsive forces from the surrounding obstacles balance out, resulting in a net force of zero. In this state, the robot has no clear direction to move and becomes stuck, unable to reach its destination. In this image, the robot is situated in a region where the forces cancel each other out, creating a local minimum. This situation is problematic because the robot cannot proceed to the goal, leading to navigation failure. Here is a simulation that shows just that. A few strategies can be employed to overcome local minima. The first is to add random noise when the robot is stuck in a local minimum. This helps the robot nudge itself out of the local minimum and then move towards the original goal. The second is to use virtual targets, which are intermediate targets set when the robot is stuck. The robot can move towards this new target, and then once it's out of the local minima, it can move back towards the original goal. The third is to employ hybrid methods of path planning. We employed the strategy of virtual targets. Here's how it works. Whenever the robot gets too close to a local minimum, which we detect when the robot's position doesn't change significantly over a few steps, a temporary goal or a virtual target is generated in a direction away from the obstacle. Instead of trying to reach the main goal directly, the robot first moves towards this virtual target. Once it reaches or gets close to the virtual target, it resumes moving towards the real goal.
The artificial potential field algorithm draws upon several foundational robotics concepts we covered during the course. First, the notion of configuration space is crucial because APF operates in configuration space to compute motion. Rigid body transformation and rotation matrices underpin how the robot's orientation and reference frames are handled mathematically. The gradient-based velocity updates in APF are derived from principles studied in our velocity kinematics. When the robot adjusts its trajectory at each step in response to environmental forces, it is essentially performing trajectory generation in real time. Finally, the way we convert the computed gradient into robot motion connects with resolved rate control, which ensures that the motion command align with the robot's dynamic capabilities. These connections show that APF is not an isolated algorithm. It builds upon and integrates core robotics concepts which we have studied in our Introduction to Robotics course. To conclude, the artificial potential field method is a simple yet powerful tool for local path planning. It is especially useful in static and well structured environments. However, due to its limitations like local minima, it is often combined with other planning strategies for more complex tasks. With the right enhancements, APF remains a valuable component in robotic navigation. Thank you.